Hello everybody. This is going to be our second YouTube video that we're going to be doing where you're supposed to watch asynchronously. Before we kind of get into the content, just a quick review as to why we're doing this. I think it's important to know our why. It's not just something that's on the stairs at our school. Why are we doing this through a YouTube video that you're watching on your own time and pace with headphones? Why can't Chris just teach it to everybody? Well, one of the reasons why is pacing. Everybody learns at a different speed, and we know that not all students go quite as quickly as others or quite as slowly as others, right? I mean, in so many things in life, we try to make it go so that it's flexible with your schedule. But when we teach one lesson to the class at one pace, sometimes it's too fast for you, sometimes it's too slow for you. And look, I understand that maybe watching a video isn't quite as entertaining and it's as interactive, perhaps, sometimes as being in class. And that's true. There are definitely some downsides to this. But ultimately, I think the pros outweigh the cons, especially on a topic that we're about to do on balancing reactions, where there's going to be a wide variety of students who either it clicks and they pick it up immediately, or whether it'll take a little while. The other nice thing is this gives you the advantage of keeping and going home and watching the video at your own time. And so let's say that it's not clicking right now and you're not overly focused, then pause the video. But you do need to watch this, okay? This is not optional. This is not something that, well, maybe I'll get to it. This is your content, and you're going to need to watch this. So that's our why. Hopefully you get it. Hopefully you understand why we're doing it. We don't do it every single time, but in certain circumstances, this is one of the better ways of, I think, trying to teach most of the students. So here's what we're going to focus on. Last time, we should have done a lesson where we would have talked about how we're now changing the word chemical change to the term chemical reaction. And that's what we want to focus on now. We need to start being able to write a chemical reaction. And I might have given you the analogy before. I'm just going to extend our page here. But I might have given you the analogy about how elements are like learning about your ABCs. And so when we're learning about how to do copper 29 with a 63 in the corner and a +2 charge, that's learning your ABCs. And eventually we want to make compounds. And compounds is when you start to make a word. That's where you then take your copper and you add it to, say, a nitrate, and you make copper 1 nitrate out of it. Ultimately, though, that's not really chemistry yet. We're just naming stuff. We'd like to get up to the point where we start reacting things with each other, and that's the goal of today's lesson, is to now have a chemical reaction, and we'd like to write what's more or less a sentence. A sentence is where we describe what is happening. And sentences, just like in chemistry and in English, they both have subjects, they have verbs, they have punctuation. We have nouns in sentences. And in this example right here, there are 4 nouns. There are 4 things that are undergoing some sort of change. The things that you begin with are known as the reactants. So the reactants are these ones right here. And the things that you end with are the products. And so these guys are the products. And those are like nouns in a sentence. You're saying that one thing and another thing are reacting with each other. We also have verbs, though. If you write a proper sentence in English, a verb is an action word. And really, the action is always the exact same every single time in a chemistry equation. It's this arrow right here. And this arrow sort of represents the idea that something is changing. Whether the color is changing, whether there's a smell, whether they're changing states of matter, but fundamentally, the chemicals are changing their properties. It's not a physical change, it's a chemical reaction. And the verb is essentially this arrow. We also have punctuation. I like to think of punctuation as being the little things like the AQs, or maybe rather than punctuation, maybe you like to think of that as an adjective. Because if you know what an adjective is a word that describes a noun. And it's really important to describe the noun with whatever state of matter it's in, the aqueous state of matter, the liquid state, the aqueous state. And we did a lesson on this in the past, so hopefully you're familiar with those concepts. If not, we'll be working on them, obviously. Our goal is to be able to continue writing our sentences. And so today, that's our goal. By the time we finish, we'd like to be able to start writing some balanced chemical reactions and have them be grammatically correct. Right? And that's the last little thing, as I've been talking about like nouns and verbs and adjectives and maybe punctuation. But they need to be correct statements, and that's our goal here. So we're going to build this lesson piece by piece. It's kind of being scaffolded, like layer by layer. We're going to get more and more difficult, so let's give it a try. Here's our first one. Sometimes we just want to write out in words what's happening. And so I've got a sentence here. Rarely will we do this, but it's kind of a nice place to start. We would write out solid magnesium metal reacts with aqueous hydrochloric acid to produce aqueous magnesium chloride and hydrogen gas. Now, before I go on, one of the things I'm going to let you know is that I'm not going to spend any time in this lesson talking about how to name or properly write a compound. Okay. Here's one of the tasks I'm going to hopefully get us to at some point. I'm going to write out magnesium. I'm going to write out hydrochloric acid. I'm going to write out magnesium chloride, and I'm going to write out hydrogen gas. And I'm not really going to spend much time talking about how I wrote all of those things. Okay. It's kind of an expectation that we're working on it. Okay. If you're not really sure where HCl came from or MgCl2 came from, that's why we're doing this asynchronously, so that if you need to, you can pause the video and ask me. Okay. But any previously learned concepts, I'm not going to be going over those every single little step along the way, because that's why the asynchronous bit helps. Okay. I will talk about a few details, though. I will point out the word allotrope. Okay, we've been talking about allotropes before. We've been talking about how you could have like chlorine with, say, 17 in the corner, a 35 up here, and a -1. This corner right here is the allotrope corner. And when we're writing out word sentences and we're trying to write our statement, we have to know the punctuation as to what it properly forms in groups of. And magnesium forms in groups of 1, so we only need to write magnesium. And hydrogen gas forms in groups of 2. And that's something that you'll pick up on over time. We can make a list of allotropes if you need, and we'll just add it to a book somewhere. We don't need to memorize it, but those are just things that you'll hopefully pick up on. We do need to have the states of matter. That's your punctuation idea, or at least the adjectives. So it said it was solid magnesium metal. Okay, solid. I'm going to add it to aqueous hydrochloric acid, so that's AQ. It's going to form magnesium chloride, which it said was AQ. And it's going to form hydrogen gas. So there's a statement. There's only one problem with this, and that's not grammatically correct. There's an error here, and it betrays the law of conservation of mass. I'm going to try to draw this out as though this was Lego blocks. So just bear with me, but we probably played with Lego at some time before here. Imagine that a red dot is magnesium. So I'm going to put magnesium on both sides here. And imagine that, let's find a new color here. Let's imagine that green is hydrogen. So I've got one hydrogen here, and since this is H2, there's actually 2 of them over here. And then I will make blue become chlorine. So chlorine is a block that goes like that, and then there's 2 chlorines that are attached to this. There's actually a problem with this particular picture here, is that it betrays the law of conservation of mass. We have started with a certain amount on the left-hand side, LHF, left-hand side. We have a certain amount on the right-hand side, and they don't match. We began with 1 red Lego block, 1 blue, and 1 green Lego block, and somehow we finished with 2 blue and 2 green. We've actually gained mass. And so what we recognize here is that this is not grammatically correct. There's an error. We've actually picked up some blue and some green. So what we're going to do to make this fit better is we must have started with an extra blue and an extra green. Apparently, we didn't start with 1 of each. We actually needed to have 2 of these. Now, maybe you're familiar with the idea of there being a little 2 in the bottom corner like this, and that does indicate how many of something there is. Like if there's a little 2 down here, that's 2 chlorines. Not of magnesium. It only applies to what's down below. What we're going to talk about today are what's called coefficients. I'll use purple for coefficients. A coefficient describes how many of the compound, the entire compound, is being used. And I would say that there's 1 magnesium being used. You actually need 2 hydrochloric acids being used, 1 magnesium chloride, and 1 hydrogen, because there was 1 of these as a grouping, 2 of these as a grouping, 1 of these, and 1 of these. And that's ultimately the title of our lesson today. It's balancing chemical equations, balancing chemical reactions. This is called balancing, where we put a 2 in front and make sure that the grammatical structure of our sentence is correct. So that is ultimately our goal. So let's keep building up. Let's keep scaffolding. I've got some slides here that kind of describe what we're going for today. The idea that we may need to put these 2's. This is a 1 in front of it, and there's a 2. And I've probably said this before, we never really write a 1. 1 is just implied in chemistry and in math often, right? But hopefully you can kind of see the picture here is that if I only had 1 hydrogen and 1 oxygen, pretend this one's not here. And pretend this one's not here. And I just tried to write hydrogen and oxygen make water. You'd see that you have 2 oxygens and now there's only 1. And there's 2 hydrogens and then there's 2. You'd see that there's a disproportionate amount. And so in order to make everything fit, in finger quotes, we need to make sure that everything is accounted for. We need 1, 2, 3, 4 hydrogens to account for 4 hydrogens afterwards. We need 2 oxygens for 2 oxygens, and that's how things fit properly. Same thing here. There's kind of a picture being shown, and hopefully you can kind of see the exact same concept going on here, is that you need to have 1 of the methanes, 2 of the oxygens, 1 of the carbon dioxides and 2 of the water so that everything fits. Just do a count again. You need 1, 2, 3, 4 of these, 4, 1, 2, 3, 4 of these. Those match. You need 1 of these for 1 of these. You need 1, 2, 3, 4 of these for 1, 2, 3, 4. Whatever you start with, you better finish with the exact same amount. Hypothetically, let's say that this thing right here, let's say we didn't think that to put 2 of them or put 2 of them. Well, then you'd see that things wouldn't be equal to each other. So now that we get hopefully we get the concept of what we're trying to accomplish, we're trying to put this little 2 right here and this little 2 right here. Now the question is, how do we go about accomplishing that? Okay, I got one more slide picture, but hopefully you kind of get the idea here. So here's the question then, how do you go about balancing these equations, right? What's the process? And this is a little bit of trial and error, it requires some practice. We'll do some games. Hopefully we'll be pulling out Lego pieces at some point. We'll actually use Lego to visualize building reactants and products. Sometimes it helps to draw it, right? Some people are very visual people. But here are some basic steps. This is what I like to do. Make a list of all your products and reactants. You kind of just balance them one at a time by adding the coefficients. Key rule here, you cannot change the subscripts. If it is written as CO2, you cannot take that O2 and make it an O3. That's not allowed. If it's H2 and it's a diatomic allotrope, you can't just make it an H3. You can't just remove something. What you can do is add 2 or 1 of something, though, to make it balanced. A general hint is this one here. Always leave your diatomic molecules till last. That's usually a good rule of thumb to try to help you balance it. And ultimately, this is really the goal. You just have to make sure that each element is equal as a product and a reactant. There's really no one set way that you balance reactions. But at the end of the day, you have to make sure that what you start with equals what you finish. And so it's kind of a puzzle, which a lot of kids kind of like. So I'm going to show you a couple of examples here. I'm going to do a few slides of examples. I'm going to do A, B, C, D on here. And then I'm actually going to pause the video, and I'm going to let you try the next couple by yourself without me doing them first. But I'll do A, B, C, D as kind of an example. It may help you to have some sort of drawing. So here, I'm going to draw it out. I'm going to draw out a hydrogen. This is an H2. And afterwards, I'm going to have an H2O. So this is H2, finishes with H2O. And then for my next one here, we're going to have oxygen. So that's O2. And that's H2O. So hopefully you can kind of see how I've made this fit here. I'm just going to try to draw it in so you can match this up. This is H2. Purple is H. I have 2 of them. I have O2. Okay, so there's those ones. And then there's water. And currently, I have 1 of everything. Does what I start with equal what I finish? And the answer is, well, no, it doesn't. You might recognize that the purples equal each other, but the greens don't. And what you might recognize is that the greens, you don't have enough greens afterwards. Now, I can't cut this oxygen in half. The first thought some kid might have, dismiss that. The first thought you might have is that, well, maybe I'll just get rid of that one, but you can't just remove a part of something, right? It's kind of stuck there. So what you're going to have to do here is instead we'll just have to add more of this compound here. So I'm going to add some more of the blue, or purple, sorry, and I'd add more of the green. And now I've made it so that the 2 green equal the 2 green over here. The problem now is that purple is totally unbalanced, but kind of playing around with it. What if I make an extra one of these? Now I can write a statement in which what we start with equals what we finish with. And that's why I like to call this like the punctuation. We've got our nouns. Everything I'm drawing here is our noun. The state of matter is like the adjective. The equal sign is like the verb. It's the action. And hopefully if we start with 4 purple objects, we end with 4 purple. We start with 2 green, we end with 2 green. Here's what that means. You must have needed 2 hydrogens and 1 oxygen to make 2 waters. And this is like a recipe. That's really what we're doing here. This is a recipe. It's no different than when you're in the kitchen cooking and you need to have 1 parts water to 2 parts cornstarch. Or, when I make rice, it's 1 part rice to 2 parts water, right? And so you now have a ratio of what to involve. Do you need 4 cups? Do you need 2 cups? Do you need a quart? Do you need a milliliter, right? And so we now have the ratio, and this has now been written as a correct statement. Okay, so that is what we're going for. Let me demo this a few more times. And as I demo it, I need to point out, look, I don't need you to get this the very first time you try it. Right? There is no expectation of me for you that you're supposed to immediately be perfect at this. My expectation is that you engage and that you try. So let me do another example here. You may just want to draw it out. We have a single iron, so I'll draw the purple as iron. We have chlorine, which is diatomic, so it comes in a 2-pack. And when we're done, it's actually going to make a 3 of chlorine and a single iron. Does what we start equal what we finish with? And the answer is, well, no, we seem to have picked up an extra chlorine, which may lead to the question, why? Well, the reason why has to do with charges here. Iron comes with a +3 charge. Chlorine comes with a -1 charge, so you need 3 chlorines to fit the iron. The problem is you need 3 chlorines, but it only starts with 2. So the only way this really works is by changing how many molecules you have. Apparently, this will work better if I then use an extra one of these. Okay, so I use 2 of these chlorines here. Problem is now it's 4 against 3. Okay, so I'll use an extra one of these ones right here. But it does come with the purple. Don't forget to draw that one. I can't just draw half the molecule. So what's happening here now is, what if I do this? What if I draw 1, 2, 3 of these? There's 6 green dots, right? And if I do 2 of these, we still have 6 green dots. Okay, the green dots are now balanced. This comes as a unit, though. I cannot modify what is inside of these things. That cannot be modified. I can just modify how many of them I have. So rather than having 1 making 1, actually 3 needs to make 2. But if 3 makes 2, they balance. The only problem is that the purple dots don't match. So what if I add an extra purple dot? Kind of draw it out like this. Now what happens is I actually need 2 irons and 3 chlorines to make 2 of these. And that's called balancing. Okay, here's the reason why we're doing this asynchronously. Some of you may have understood that and you go, wow, okay, that totally makes sense, Chris. Cool, keep going. Others of you may be like, whoa, you just drew dots everywhere, Chris. Why are you drawing all these circles? I'm lost. Slow down, Chris. I don't get it, right? Like, cool. If that's you, that's fine. This is why we're doing it this way, so that you have the ability to pause the video, so that you have the ability to stop, put up your hand. Ideally, you're watching this either in the classroom or someone very close to the classroom, so you can ask me for help. Ask for help, right? Don't just leave it. That's why we're doing it asynchronously. Let's try another example. Now, what you may discover is after a while, it's really annoying drawing out molecules, especially this one right here. We don't even know how to name this one yet. Maybe you do. Maybe you recognize it. It's part of biology and plants. That's as much as I'll say. Maybe you'll recognize it. Anyways, with this chemical right here, maybe I don't want to try to draw it out. So here's another option. This is what I like to do. I like to make a before and after chart. So B and A for before and after for all of the compounds that I have. And it looks like I shouldn't say compounds, I say elements. I have to account for carbon elements. I have to account for oxygen and hydrogen. And I just make a running list of what's there. So currently it looks like we start with 1 carbon. And on the right-hand side, it looks like afterwards we finish with 6. Okay, it's clearly not balanced. I will come back to that. For oxygen, it looks like we have 2 right here, plus 1 more right there. So we're actually starting with 3. And afterwards, we have 2 plus 6 for 8. And finally, for hydrogen, it looks like we start with this little 2 amount right here, and we finish with 12. If I lost you as to how I got those numbers, pause your video, please, and let me see if I can explain it better. But I'm just making a before and afterwards chart. In order for us to proceed, these numbers have to equal each other. And they currently don't. So I need to try to find the best way I can to do that. How do you make 1 become 6? I can't just hack the 6 off, but you know what I can do? What if I put 6 of these here? Put a 6 there in front. Well, now I have 6 of everything that's here. It affects only the before numbers. I now have 6 carbons. And it ends up multiplying when you're done, really. 6 groups of 2 makes 12 oxygen, plus 1 more makes 13. But you know what's nice is that now I've balanced my carbon. So at least I have something that's balanced. And I can kind of do that same thing here with hydrogen. I need 2 hydrogen to turn into 12. Well, I just need to bring more to start with, right? I can't just magically make more. I have to multiply. I have to clone this thing in a way. So what if I clone this and put a 6 here? Well, now 6 groups of 2 means that I have 12 hydrogens. It also messes up my oxygen like crazy, though, because now I have 6 groups of 2, which is 12 oxygen here. That's a 12. And I have 6 groups of 1, which is 6 more. So I believe we're now up to 18 oxygens total. But the good news is my hydrogens are now balanced. Now, I have to try to figure a way to fix this over here, because it looks like my carbons and hydrogens are all good, but my oxygens aren't. Here's what I don't want to do. I don't want to put a number in this spot right here. Because as soon as I put any number in this spot right here, it buggers up the carbon and hydrogen. And didn't I just spend time fixing those? So I don't want to mess that up. So I think I need to leave this one the way it is. That's kind of like the logic behind it. And by leaving it the way it is, I'm going to put a 1 there. So it means the only thing I can mess around with is this oxygen over here. I can change the groupings of oxygen that we produce. And so I'm just going to kind of like work backwards and say we know that we needed to have 18 oxygen total on this side, right? Because 12 and 6 made 18. This thing right over here is bringing 6 though, right? Isn't there 6 coming from this one? So if I want the grand total to equal 18, this guy right here better bring 12. And they come in packages of 2. The allotrope is in 2s, so it must mean I need 6 of them. If I bring 6, 6 by 2 is 12. Add 6 more, we have 18. Everything's balanced. And now we have the proper punctuation for our sentence. We're getting closer to being able to do some chemistry now, because now we're able to talk about what's there, and we can actually write a statement of something happening. I might have given the analogy of recognizing music. Right? Just being able to find one note really isn't a whole lot of music yet, but we're kind of writing now. This would be like composing music. We're now describing what's going to happen. So let's try one more example for me, and then I'm going to have you try some examples. I'm going to pause the video. I'm going to have you pause, try the questions, and then we'll see how you can do on your own. But let's do one more example here. This is, again, my scenario here. I like to make a list of before and after. And then we have carbons, hydrogens, and oxygens to account for. Currently, it is 4 to 1, it is 10 to 2, and it is 2 to 3. So nothing is balanced. Let's start. Now, the only way I'm going to get those carbons balanced, which was 4 to 1, is by putting a 4 here. And what it'll do is it'll make it 4 carbons afterwards, because this C4, where the 4 only applies to the C, gives you 4 carbons. And this 4C right here means the 4 applies to the whole molecule, but you'll still have 4 carbons. But we buggered up oxygen. 4 of the entire molecule, so the molecule is the CO2. So we have 4 of them. Imagine I wrote in another CO2, another CO2, another CO2. I actually have 2, 4, 6, 8 oxygens, plus 1 more right here makes 9 oxygens. So oxygens got buggered up, but carbon's done at least. Let's talk about hydrogen. Hydrogen, we've got 10 over here, but there's only 2 over here. But what if I started adding more waters? So that's 2, 4, 6, 8, 10. There, I managed to get enough hydrogens by putting a 5 here. By putting a 5 here and having 5 of them, I now have 10 hydrogens. So I now have 10 hydrogens. But it's buggered up the oxygens, because now I think I had 8 oxygens here, and now I have 5 more here, which means that my oxygen is up to 13. But the good news is I'm matching on some of the stuff. Okay, so what's left? Oxygen. I have 13 after and 2 before. I need to change the ratio of what's going on right here. I definitely don't want to change the C4H10 just yet. I want to leave it as 1, because if I change this, it changes these guys. So for the oxygen, they come in 2s. How do you take a 2 and make it equal to 13? And the answer is 6.5, which leads to a problem. I gave you the analogy of probably buying something like toothbrushes or something like that in a 2-pack versus a 1-pack at the store. The problem is that you want 6.5 packages of 2 to get to 13, but you can't buy half of something. Well, there's a way we fix this. Although this kind of seems nice, you can't have half of an oxygen molecule. So we are done. I can erase this for right now. This is balanced, right? Just check the math. 1 by 4 is 4 by 1. 1 by 10 is 10. 5 by 2 is 10. And then for oxygen, 6.5 by 2 is 13. There's 8 here and 5 more for 13. They match, but you can't have half an oxygen. Here's what you do. You double the recipe. Just like in cooking. If the recipe isn't necessarily working for you with what you have, let's say that you need to use 6.5 boxes of flour, but you don't want to use 6.5 boxes of flour because you don't want half a box left over. Or maybe you can have half a box of flour, but you can't have half an egg, and you're like, you need to use 6.5 eggs. I can't use half an egg. Double the recipe. Use 2 of these. Use 13 of these. Use 8. And use 10. And now it should be balanced. And I challenge you, just kind of double check. Either like write it out like this. Write out C, 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 H, 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 H. Oh my goodness, this is ridiculous though. Okay, there's 1 of them. And then I could write out O, 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 O 13 times. You could actually draw this out and make sure that what you start with equals what you finish with. Right? But you need to find some sort of way of keeping track of that for yourself. So here we go. We've done 4 examples. I've shown you the concept of balancing. there's really no one right way of balancing. You either kind of you have it correct when you're done or you don't, right? You either have the punctuation in proper places or not. But you need practice. So here's what I'm going to do. On this next slide right here, I've got some examples. I'm going to pause the video. This is going to be your warning. I want you to pause. I want you to try it. Even if you don't understand, I want you to just try whatever it is you can possibly try. I want you to call me over. I want you to get help. We'll go get Lego blocks. We'll build stuff if we need to. We'll draw dots if we need to, but we'll try to get a sense of how to balance. Okay, so this is your warning. I'm going to pause the video, and when I'm done, I'm going to unpause the video, and the answer key will be up here. And then you can check your work. Okay, so here we go. Video's paused. Okay, so now the video is unpaused. One of the things that I've made a mistake on this slide, and I never change it because it's always a good talking point, is that right here, right where I'm going to put the eraser, I won't erase it. Well, I will erase it right there. You can see that. I actually made a mistake. I never change it because it goes to show why it's really important for you to know how to do all of the previous background knowledge, because it's written as H3 right here. But hydrogen doesn't actually come in an allotrope of 3 ever. It only comes in allotropes of 2, which means there should have been a 2 here, which changes how you balance it. You may have discovered, and hopefully you told me this, you pointed this out to me when I paused it, hopefully you discovered that F is actually almost impossible to balance unless you actually write the 2 here. It really just doesn't make as much sense otherwise. You can try to balance it, maybe it'll work, but if you ever write a molecule incorrectly, balancing it just goes out the window. So anyways, long story short, here's your answer key. If you have any questions, let me know. Please stop the video. You can see this is why we're doing it asynchronously, so you have the ability to pause, rewind, fast forward. Some students, this might have taken 4 minutes for. Some students, this may take you 40. I don't care how long it takes you. Right? It's not a race. Understanding something is not a race. You've probably heard this analogy before. I'll use it right now because we're finishing it with my 2-year-old. But there's some kids that they get potty trained by the time they're 2, and there's some kids by their 3. Some kids are potty trained by the time they're 14 months. And I have 3 kids. They all potty trained at different times. One was like a year and a half. One was 2.5. One was 2. Who cares? Hopefully all of you are potty trained. Hopefully all of you know how to go to the bathroom by yourself, right? And all that matters is that you get there, right? So who cares whether it happens in 4 months, 4 minutes, 4 days, right? Our goal is learning. So anyways, long story short, if you need more time, take more time on this. If not, I'm going to proceed though. What I have here is one more practice slide. I'm not going to spend the time on it right now, but you can if you'd like to. I won't put the answers up, but what I will say is that if you'd like me to look over your work, I'd love to. I'd love to give you some advice. I'd like to help you out with this. Okay. But that's one of the skills we've learned so far. Now, here's the problem, though. That only worked because I told you exactly what was going to happen. I told you that sulfur and oxygen would make sulfur dioxide. But sometimes when you're writing a sentence, we get the start of the sentence, but we really don't know how it's going to finish yet. And that's really where the creativity comes in. I love the analogy with English here, or with music. We're now starting to write and compose. And it's one thing for me just to write and copy down what's already there, but sometimes we have to make a prediction about what will happen. I want to show you where we're going to end our lesson here. I'm going to fast forward in our slides to here. This is ultimately our goal. I'm going to start off by giving you an intro stem, and it's going to be your job to figure out the question mark on the other side and predict what's going to occur. All right, this would be like in English where your teacher gives you the beginning of a poem or a story, and you have to try to figure out how you want to finish it. Or it'd be like in music where you're composing and you have the first line, the da 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 da, and then you got to figure out what are you going to do with the rest, right? How are you going to finish it, right? That's what makes it unique. That's what makes it composition. That's what makes this more than just memorization. So in order to figure out what something is going to create, this is not the entire set of rules, but these are some common reaction types. And it will help us to be able to get a sense of what is probably going to happen in a chemical equation. There are 5 types of chemical reactions. I'm going to walk you through all 5 of them first, and then we're going to go through and practice some balanced equations. Here they are. One type of common equation is a formation, where an element, let's call it A, another element, let's call it B, merge together and form a compound, let's call it AB. Look at this. Sulfur and oxygen make sulfur dioxide. This was an element. This was an element. It now makes a compound. That's one type. The opposite of that is a decomposition, where a compound, let's call it AB, breaks apart into elements A and B separately, like if water could separate into hydrogen and oxygen. That's 2. 3, a single replacement. This is all about flipping places. And I've actually already got it written out as A and B and C. This is a common structure where A and A and B are flipping places. Can you see how it used to be A by itself and BC was joined? And now B is by itself and AC is joined. A good example of this is just taking turns on something. Let's say that I have a 2-player game. My daughters are playing video games at home and there's a 2-player game. So this is Kinsey right here, not playing. And Cami and Casey, those are my daughters, by the way. Kinsey is not playing and Cami and Casey are playing a game. And eventually they have to take turns, they switch. So now kid B is now not playing at all. And kids 1 and 3 are playing, right? See how there's a switch there? That's a single replacement. Now that can happen with A switching with B, where B is a metal. It can also happen where these ones can switch. So if I numbered them like 1, 2, and 3, I could have one switch with 2 or I could have one switch with 3. It just depends on whether it's a metal or a non-metal or not. Keep in mind, you can only switch out with the same sort of things. Metals switch with metals, non-metals switch with non-metals. There's also a thing called a double replacement where you do like a full double swap. The best analogy I can think of for this is if people are, say, dancing and you decide to switch partners. So A and B are dancing together, C and D are dancing together, and what ends up happening is A swaps with C and B swaps with D in a way, right? So what ends up happening when you're done is that A is now dancing with D and C is now dancing with B. And there's basically there's a double switch, right? It's not just one switching with one, but everyone has a new partner to work with here now. The final one is one that you're probably familiar with. It's called combustion. And combustion is exothermic. We discussed how it always is a production of energy. It blows up. And combustion has a very similar pattern. It always involves oxygen plus some sort of hydrocarbon combination. We write X and Y because we don't actually know what proportion they're in. But we take some sort of carbon, add it to oxygen, and make carbon dioxide and water. Okay. So those are our basic 5 reactions. Let's go back through and practice writing some balanced equations as a group. So here we go. We need sulfur and oxygen making sulfur dioxide. This is where your allotrope knowledge really helps. There's a slide in our notes previously that talks about allotropes. You may want to find it at some point. But sulfur comes in groups of 8, actually. And according to the periodic table, sulfur is probably a solid because that's its color on the periodic table. It's probably black in color. Oxygen, however, as an element, comes in groups of 2. That's its allotrope. And oxygen, according to the periodic table, is a gas. Finally, we're going to make sulfur dioxide. And the way that you name sulfur dioxide is SO2. I won't go over that in this lesson. If you don't know how I came up with that, pause the video and ask, okay? And sulfur dioxide will probably be a gas because most molecular things are gases. Now, I don't overly care if you make any mistakes with the states of matter because sometimes those are a little bit tricky. Here it's pretty clear, though. You can actually look up most of this information and be fairly confident. You definitely have to get the allotrope number right. Otherwise, it buggers up the whole thing here. Our last step, though, is we need to balance it. So I'm going to go a little bit faster on balancing now because, again, that's the whole point of the YouTube video. For those who need to go at a faster pace, you can. For those who need to slow down, then slow down. Here's what I would do. I'd say you have 8 sulfur and 1, and I put an 8 in front. It's now really 1 by 8 and 8 by 1. That's 8. 8 on both sides. This 8 applies to the entire compound, though. So it applies to the 2 oxygens that are there. So 8 groups of 2 oxygen is 16. To make this 16, I'll make it 8 by 2. And now it's balanced. And we've now written a balanced equation. Let's try this one. First, we need to start writing it out. It says water turns into hydrogen and oxygen. We know what water is. It's H2O. And its most likely state of matter is probably liquid, but it could have been solid or gas. I don't really know, but that's reasonable. Hydrogen comes diatomically. That's its most common allotrope. And hydrogen, according to the periodic table, as an element is a gas. Oxygen is also diatomic, and it's going to be a gas, according to your periodic table. So we always want to write a state of matter. We just want to do our best to make sure that's the appropriate one. Take as reasonable or as educated as a guess as you can, and sometimes you can really look it up. Look it up if you can. Last one is that this is not balanced. You'll notice that there's a discrepancy in oxygen. Hydrogen is 2 to 2, but oxygen is 1 versus 2. So if I put a 2 right here, that balances the oxygen, but not the hydrogen. If I put a 2 there and a 1 there, we're good. However, we don't usually write the 1s, so don't bother writing a 1. There we go. Like I said, I'm going to blitz through this I don't have any wait time. Wait time is a term for teachers where we kind of pause to give you time to process. If you need time to process, press pause, because I'm going to keep plowing through these. Here's another one. It's magnesium. That's Mg. Magnesium comes in allotropes of 1. I won't write that out, and it's solid. Then we need silver nitrate. Again, I'm not going to talk about how to make the molecule silver nitrate. If you need help on that, let me know. We're working on it, hopefully over time. That's silver nitrate. Now, we need to know our periodic, you need a data sheet because you need to be able to know whether this is aqueous or solid. We would have talked about this at one point in our in a lesson. I'm going to find you the chart really quickly here in a previous lesson just so you can see what I'm referring to. We learned about a chart that looks something like this. And if we're trying to figure out whether something is going to be aqueous or whether it's going to be solid, this chart can also help us in figuring out states of matter. So I believe it was silver nitrate. And according to that, silver nitrate would fall into this category right here because there's the nitrate, and silver is not down below. I'm not going to be showing you this chart every single time though, okay? If you need to, pause the video. That's why we're doing it this way. But silver nitrate would be aqueous. Then it's going to produce, I'll use a big arrow here. I'll have to go kind of below to make this fit. It's going to produce silver. Silver comes in allotropes of 1 and should be solid. And it's going to make magnesium nitrate, which will be Mg bracket NO3 2, and state of matter will be aqueous. As always, if you have no clue where I got all that information from and you're just lost beyond all lost, ask. That's why we're doing the YouTube video this way. Okay, because our main focus of the YouTube video is to help you balance. Okay, so let's spend more time on balancing rather than writing out formulas. If you struggle with the formulas, ask for help. Here's what I recognize. I like to do it this way. Magnesium and magnesium are actually balanced, and silver are actually balanced. But there's one nitrate, and there's a nitrate with a 2 here in the corner. Nitrate's not balanced. I'm going to put a 2 here. Nitrate's now balanced. Problem is silver's not, but I can fix that by putting a 2 in front of the silver. And now we've written ourselves a nice balanced equation. We're going to play some games. We're going to do some puzzles. We're going to play with Lego. We'll do worksheets. We'll do quizzes. We'll do all sorts of activities. The goal right now is not to expect that you're going to have it perfectly down pat. I don't expect you to be able to do this on your own entirely yet. Just keep watching some examples, right? Just watch. Right? Write down if you want to. Just watch. And we'll get there. Okay, just engage in the process. Let's try this one. Chlorine. Chlorine, it's chlorine by itself. It's an element. That must be Cl. Chlorine is diatomic in terms of its allotrope. You just need to know that one. Write down a list somewhere. Chlorine on the periodic table is in a gas format typically. Silver bromide is AgBr. If you're struggling with how to write that one, pause the video and ask me for some help or slow down. Looking at the table, silver bromide is probably going to be solid because I can see that on that table that I showed you a few seconds ago. It looks like this is going to form bromide, which bromine is also diatomic. However, this one's a bit different here. Bromine is actually a liquid at room temperature on the periodic table. So I'm going to put liquid down. That's the most likely one to use. And then finally, silver chloride is AgCl. And looking at that same table that I mentioned earlier, it looks like it'll also be a solid. There we go. Last step is the punctuation. We have our nouns right here. We have our adjectives right here. We have our verb as the action of a chemical change. The question is it punctuated properly? And it's not balanced. Because you have 2 chlorines making 2, 1 bromine making 2. Right? So you have 2 chlorines making 1, 1 bromine making 2, and silver's balanced. And how you fix this is you put a 2 here in front of the silver bromine, and that doubles up the one you were missing here the whole time. And if you put a 2 right here, it fixes both problems. The chlorine that's 2 is now doubled, and the 2 silver right here matches the 2 silver you wrote there. Let's keep going. Lead nitrate. Lead nitrate is Pb. And then we didn't know which version of lead it is, but there's a Roman numeral 2 here. That means it'll be NO3 twice. Because that's the lead 2. The 2 kind of ends up going here if you like the crossover method. According to my table, nitrate's pretty much good with everything. It should dissolve. It's not an exception. I'm going to add some sodium iodide. That gets written as NaI. And according to that table that I mentioned earlier, sodium iodide is also an aqueous substance. It's going to make me lead 2 iodide, which is PbI2. And according to my table, lead is actually the exception. Lead is actually in the solid column of that table when you're with iodide. It'll also make sodium nitrate, which is NaNO3. Now, right now, I am blitzing through this. And I'm actually doing that on purpose. One, because I can, because you can pause if you need more time. But two, because I need to let you know that this is going to be the expectation going forward. I need you to become fluent. Okay, just like you're fluent in the language of English. For those of you who understand music and analogies, right? If I were to ask you, if this is a bar clef right here, maybe you know music, maybe you don't, but if I were to write a bass clef right here, if I were to ask you what note this is right here, you can't take 10 years to figure that out when you're trying to solve a piece of music, because eventually there's going to be all sorts of other stuff going on in the music, and you need to be able to understand how to play this piece of music, however it gets written. And so you can't always be going, okay, that's F, that's E, that's A, that's F sharp. Like you need to be fluent in it. And one of the only ways to really help students really get to go fluent is to go at a reasonable pace. Okay, so slow down if you need to. Obviously, slow down if you need to. But what I'm trying to say here is that I need you to get to the point where when I talk about sodium nitrate, you immediately know what that is. If I say potassium iodide, you know that it's Ki, and you're fluent on it. You get it instinctively. Otherwise, you'll never really be able to go much further in chemistry. Okay. You do the same sort of thing often in learning a second language. If you take a Spanish or French or German classes, often one of the best ways of learning is to try to become fluent is by immersion. That's why we call it French immersion, right? And the goal is that you're there with somebody who's going to only ever speak French to you, so that you hopefully will pick it up faster, because it pushes you, right? It's going to be strenuous. So anyways, that's why I'm going fast, by the way. It is on purpose. I know that it's on purpose. I know it might be too fast. Okay, for the balancing part, I'm just going to look at what I see as a flaw. There's 2 iodides to 1. I'm going to put a 2 here. I now have 2 sodiums to 1. I'm going to put a 2 here, and I think all my problems are solved because 2 nitrates, there's a little 2 after the nitrate. We're good. Last one, hydrocarbon combustion. Methane is one of the oddball ones. You're supposed to just be able to know what methane is. And honestly, if you don't, ask your Google phone what methane is. That's fine. That's very reasonable. You don't need to memorize knowledge, remembering sort of facts. You need to have application skills. So methane is CH4. Methane, you might know, is a gas. You might also take a guess at that because it's molecular. Oxygen comes in diatomic allotropes. Carbon dioxide, hopefully you know, is CO2. Probably a gas because it's molecular. Water, I have no idea what state of matter it is. I'm going to go with a gas just because everything else is a gas. So maybe this has been heated up to the point where it's past 100 degrees Celsius. But honestly, if you put a liquid here, that's reasonable. You know what's not reasonable? Putting nothing here. If you put nothing there, I will flag it for you and ask you to do it again. But if you'd have put a liquid here, I'd have been fine with it. That's fine. Okay, next step, we need to balance it. I see 1 carbon to 1 carbon. Sweet. I see 4 hydrogens to 2 hydrogens. Let's put a 2 in front. That's good now. I see 2 oxygens here, plus 2 by 1 is 2 more. I see 2 oxygens here and 2 here. That's 4 total. Right? 2 plus 2 is 4 oxygens. I need 4 here. Let's put a 2 in front. That'll give us 4. 2 by 2 is 4. Okay, let's do a quick recap. Here's what we've covered so far. We've talked about the principles behind how to balance. We talked about why it's necessary. We've given an analogy of verbs and adjectives and punctuation. But why is all this necessary? Well, for this last slide right here, it's for this bit. We would ultimately, as chemists, like to be able to predict what's going to happen. Scientists should be able to make predictions, hypotheses, be able to take a guess as to what's going to occur and be right. Right? True science says, I think that if I drop a pen, it's going to fall, and it does. Right? I mean, we'll talk about climate science in our next unit. But there are some problems with climate science because you should be able to make a prediction and have it come true. If you predict that New York's going to be underwater and it's not, there's flaws with your science. Now, I'm not saying it's entirely wrong, but I mean, that's the hallbearer of science, is that through the scientific method, you're able to make a prediction, right? And that's our goal here, is that you need to be able to make an accurate prediction as part of science. If not, it's not really science. I'm not saying it's not useful. I'm not saying it's wrong necessarily. I'm just saying that's the hallmark of science. We want to be able to take some starting things and make a prediction as to what they're going to finish with. So I'm going to do 5 more examples, and then that's actually going to be it for our lesson. Then we're going to work on this over the next little while. So the first thing we want to figure out is, well, what kind of reaction is PbBr4 going to undergo? And if you look back through the different types that we had there, really the only one that really fits is that if we have a single compound, maybe it could break apart into its element. So it could break apart into lead. Lead comes in groups of 1 and is probably solid. And it could break apart into bromine. Okay, what's bromine's allotrope? 2s. Bromine state of matter on your periodic table is probably like liquid. Often it's drawn with like a blue color for liquid. It's not balanced because of the bromines, but if I just put a simple 2 in front of it, now it is. And there we go. This is now actually starting to do some science. We've now made a prediction as to what's going to occur. It's like free writing and creative writing. It's like composing in music. We're now getting to the stage where we're beginning to actually accomplish and do something and make a prediction about what's going to happen next. Eventually we'll get into a lab and we'll actually combine chemicals and see what they do make and see whether it matches our predictions. Let's try another one. NiNO3 and Na2SO3. This is going to be double replacement, and I can tell that because I have a compound with a compound. These things are going to do like the old double switcheroo. What will happen is the nickel will go with the sulfate. Now, this one needs a few extra seconds to talk about. Based on what I see here, this nickel is the +3 version of nickel. And I know it's the +3 version because the NO3, there's 3 of them. This SO3, though, is a -2. And I know that because there's 2 sodiums going with the SO3. So I have a 3 versus 2 conundrum. So without getting into too much of it right here, if this is a nickel 3, we're going to need 2 of them. And this SO3, we're going to need 3 of them. Okay. If I lost you on that step, ask for help. That's why we're doing it this way. Looking at the table, it looks like anything with SO3 is usually a solid. So I'm going to put a solid state of matter here. Finally, when we do the other switcheroo, it looks like the sodium will go with the nitrate, and that'll be NaNO3. And according to my table, that's AQ. Last step is some balancing. I see an incongruency here on my nickels. My nickels, I could put a 2 there. Now my nickels are balanced. I then would have 6 nitrates. Over here I only have 1, so if I put a 6 in front, that would give me 6 nitrates. There'd be 6 sodiums now. There's only 2 over here, so if I put a 3 in front, 3 by 2 gives me 6. And if you do a double replacement reaction like this, what's really cool about it is that 3 sulfates should match up with the 3 sulfates I have down here, and we're now done. And we've now made a prediction about what's going to occur. What we'll eventually do then is in the lab is I'll give you 2 compounds, we'll mix them together, and you would then predict to have some sort of solid show up as we combine them together. Let's try another one. Zinc and sulfur. Now for this one right here, I wrote it out in words. I did that on purpose just to remind you of, you may have to actually from words put it into a symbol. Zinc is Zn, comes in groups of 1, we'll skip the 1 and it's solid. Sulfur's got a really cool allotrope. Sulfur comes in groups of 8. They call them flowers of sulfur actually. Sulfur's standard form is usually solid, it's usually black on a periodic table. And when you combine these together, it looks like you're going to make a compound of zinc and sulfur, zinc sulfide, because this is a +2. This is a -2. So they'll just fit together just perfectly. And if you look at that table, sulfide is on there. It's only soluble with group 1, group 2, and ammonium. So it looks like this thing should be a solid. Last step, we need to balance. And really the biggest problem with balancing is that you've got 8 sulfurs here. So if I put an 8 here, that takes care of the sulfurs. If I throw an 8 in front of this one, it takes care of the zincs. There we go, we got our example. All right, I'm going to erase it. So just rewind it if you need to see it again. I say that a lot. We're almost done, by the way. We're getting close to the end of this lesson. Let's do the next one, copper and gold chloride. Copper is Cu. Copper is usually solid according to our periodic table. And gold 3 chlorate, if made properly, is AuClO3 with 3 of them because of the 3 charge on the gold. Gold is +3, and chlorate is -1, so you need 3 of those. According to the table, chlorate is soluble with pretty much everybody, so it's in the aqueous table. All right, we got to figure out what this is going to combine to produce. Well, based on the different reaction stems that we've had, one of the only ones we haven't covered yet is single replacement. It's where you basically take turns, right? This is my daughter's playing video games, and copper and gold are going to change places because they're both the metals. So it means we're going to get copper going with the chlorate. I have to pause for a second here because we need to figure out what charge copper has. Copper actually has more than one charge. It's one of those multivalent ones. So since we don't know which charge it's going to make, go with the most common one. Copper, its first charge is the +2. So if copper is a +2 and chloride is a -1, you're going to need to have a 2 around the outside of it there. Okay, that's how you properly build that compound, and that should be aqueous. Gold will be what you kick out otherwise. Okay, so let's talk through what happened there. Copper changed places with gold, so copper's now with the chlorate, gold's kicked out by itself. Gold comes in groups of 1, that's its allotrope, and it's solid according to the periodic table color scheme. Copper, its most likely charge is +2, and when fitting that with chlorate's -1 charge, you need 2 of them to make it fit. Now we need to balance. I'll use another color for balancing. To balance it, I notice a real big problem between the chlorates. We used to need to have 3 of them to combine with gold, because gold is a 3 charge. But you only need 2 to combine with copper, because copper has a 2 charge. So in order to balance that, the lowest common multiple of that is 6. So I'm going to put a 3 here and a 2 here. Because a 2 by 3 gives you 6. And 3 by 2 gives you 6. So our chlorates are actually balanced because we have 6 of each. And since I'm at the end of the lesson, I'm not really showing all the little steps, but I mean, I could draw pictures of these if I needed to kind of keep track, or we could grab Lego and play with that. Okay. So let me know if you need that. Because otherwise, well, if there's 2 gold here, let's put 2 gold there. If there's 3 copper here, let's put a 3 in front of copper there. And now it's balanced. This is the skill we want to work on. It's not an easy skill. It's not something that I expect you that you're going to have by the end of this video. Okay, I do not have that expectation of you. I expect that you have questions. I expect that you're going to have challenges. That's fine. That's the point. That's why we're here. Let's do one last one, then we're going to call it a day. We have C6H14O2. This is combustion. Combustion always makes CO2 and water. And carbon dioxide is probably a gas. And water is probably going to be in the exploding version, so probably gas. It could be liquid though. To balance, I see 6 carbons, but only 1 here, so I'm going to put a 6 there. I see 14 hydrogens, so 7 groups of 2 would take care of that. Here's where we got a bit of an issue. 6 by 2 is 12 oxygens, and 7 by 1 is 7 oxygens, which when you add them gives you a grand total of 19 oxygens. But oxygen has to come in a 2-pack, which means it can either be 2, 4, 6, 8, 10, 12, 14, 16, 18, or 20. It cannot be 19. Well, it can if you use a half pack. If you do this by 9.5, 9.5, it'll work. The problem is that you can't use half of an oxygen, so we have to double the entire reaction is how we solve this. So let's upscale this to 2, double this to make it 19, double this to make it 12, double this to make it 14, and we have ourselves a balanced equation. Okay, so we're at 52 minutes right now. We're going to wrap up the video, so it's hopefully well under an hour. I don't know whether you're going to finish this in class. That's not my expectation. My expectation, though, is that you've watched up to here. Okay. I almost feel like I should put a secret code word at the end and say, did you watch right to the end? The special code word is salmon. And then if I ask you, did you watch, and you know the code word was salmon, then that's my test. But I'm not going to do that because that's not how we run the class. Okay. But I hope you watched all the way up to the end of the video here because you need to. You need to see this for the first time. We're going to practice this. I'm going to have worksheets. We're going to do puzzles. We'll get out Lego. We will do any sort of activity that's kind of helpful in helping us learn this. Okay. You may want to work on it on your own for a little bit here. So I have some examples that you can try where the goal is I've given you the start. Your job now is to take everything we've learned, and I mean it really builds on each other. You need to know your protons, neutrons, and electron stuff. You need to know how to name things. Oh, I will close that. You need to know how to name things. You need to know how to make your compounds. You need to know your multivalents and your polyatomics. This is like a Jenga tower. If there is one thing that you don't know how to do, this whole thing topples down. So in the reflection that I'm going to ask you to write when you're done with this video, please tell me some of the things that you can do. I think my reflection question says, discuss your understanding. So tell me what you understand from this and tell me what you don't understand. The stuff that you do understand is awesome. We'll focus on that. We want to celebrate it. The stuff that you don't understand, we can't leave it. We have to start to figure it out. So I believe that's it for my lesson. Topic 7 is going to be our last one, and then actually we're done with chemistry. So as always, if you have any questions, comments, concerns, conundrums, curiosities, criticisms, or complaints, you can always talk to me, okay? Even the criticisms and complaints, I can take them. We're doing this very purposefully with the YouTube video. I'm kind of rambling here at the end, so you can probably turn it off now. We'll talk in person, okay? Thanks for watching the video, everybody.